Let's work this problem to apply the principles that we just learned about calculating pump efficiency. In this problem, we have a pump that's connected to an electric motor. The motor is supplied with 1 amp of current from a 12-volt DC power source. The apparatus runs steadily for 30 seconds and the following measurements are recorded. We have a volume of the fluid collected at 0.5 liters. The diameter of the exit tube is 3/16 of an inch, and we have a height of the fluid above the reservoir of 30 inches. We're also given some useful conversions that we may use while we work this problem, and we're asked to find the fluid velocity at the exit in meters per second, the flow rate in liters per minute, and the system efficiency. There's a hint that's included in the problem, and it says it's very helpful to convert all U.S. customary units into SI units before beginning the solution to avoid complexity. That's a very useful tip. All of these calculations will be done in the metric system because we're using amps and volts, which are in metric. And so we need to make sure that we have all of our distance units or all of our weight units or anything like that in the metric system. So the way I would start working this problem is I would start to identify the known information that's given to me in my problem statement. I know that I have 1 amp of current, so current is equal to 1 amp. I know that I also have a 12-volt DC power source, so my volts is 12 volts. I also know that I have a volume of the fluid that's collected is equal to 0.5 liters. Now this right here is a red flag for me because I know that when I'm going to be doing my calculations, if you recall from our unit analysis that we were doing, we typically wrote volume as meters cubed. In order to do this, you need to make sure your volume is written as meters cubed. At this point, I would do my unit conversion and write this as meters cubed. That there is 0.001 meters cubed in 1 liter, which is equal to 0.0005 meters cubed. Now I'm going to continue writing my known information. I know that I have a diameter of the exit tube equal to 3/16 of an inch. Again, there's a red flag here because that's in inches, and I want this to be in metric or SI units, and so I know that there are 2.54 centimeters in 1 inch, and I know that there is 100 centimeters in 1 meter, which is equal to 0.00472625 meters. Notice these numbers start to become a little ugly and not easy to work with, so you need to make sure you take the time to write down everything very carefully and clearly. And finally, I know the height of my fluid above the reservoir, which is my pump head, is 30 inches. Again, red flag because that's not in meters, so I need to multiply that by 2.54 centimeters in 1 inch. That's just the unit conversion that I've memorized, 2.54 centimeters in an inch. That's easy to remember, and you might want to memorize it as 1 inch is 25.4 millimeters, or you might want to memorize it as 0.0254 meters in 1 inch. Either way, as long as you correctly convert it into meters in order to get the value you need for your calculations. The pump head is 0.762 meters. And now you have all the known information in the form of SI units, which you can then use to do your calculations. So the first thing we're asked to find is the fluid velocity at the exit in meters per second. So I'm going to do part A, and I know that velocity is equal to volume over area times time. Now I don't have the area, so I'm going to have to do a side calculation in order to find area. So my area is equal to pi over 4 diameter squared. Many of you are probably concerned by this form of the area equation. You may be used to pi r squared. Notice that the radius is equal to diameter divided by 2. If I replace radius with diameter divided by 2, I have pi times diameter over 2 squared, which is pi d squared over 4, which is the version of the area equation that I've chosen to use. I want to take this second to talk about why you would use pi d squared over 4 versus pi r squared. Take a second and think about why we might use diameter as opposed to radius. If you came to the conclusion that diameter is easier to measure, you're right. You can easily measure the diameter, whereas trying to measure the radius of a circular object is very difficult, trying to find that center section of it. And so typically in engineering, you will see us use this form of the area equation because we can more easily measure diameter. So get used to seeing area written in terms of pi over 4 d squared, because you'll see this a lot in many of your other classes. Let's continue and calculate the area. My diameter I calculated to be 0.004765 meters squared, which then calculates to be 0.000017814 meters squared. Again, these numbers are ugly, but so you really have to take care of writing them down correctly as you work the problems. So now we have our area, we have our volume, which was 0.0005 meters cubed. Notice we have meters cubed here and we have meters cubed for our area. This confirms to us that we could not use the liters version of our volume that we had given to us in the problem statement. Then we put our denominator with our area and we multiply that area by time. Our time is 30 seconds, which was given to us in the problem statement. And we calculate velocity to be 0.9356 meters per second. Now that is a really hard number to visualize. And so maybe when we calculate our flow rate, which is part B, it might help us understand what that value actually is a little bit better. So let's go ahead and calculate part B. Part B is to find the flow rate. Flow rate is volume over time. And I want it to be in liters per minute. That's what was asked of me in the problem statement. I got my volume in liters, so I can just simply write 0.5 liters. And I know that it was 30 seconds, so I have volume per time, liters per second, and now I can convert seconds into minutes. There's 60 seconds in 1 minute, which gives me 1 liter per minute. Now this is a number that is a lot easier to understand. You can visualize a bottle that holds 1 liter of liquid. If you hold that bottle under the exit tube, it would take 1 minute in order to fill that liter bottle. That's pretty slow, and so we can kind of predict that our efficiency will probably not be very good, but that's a lot easier for us to visualize 1 liter per minute as opposed to 0.9356 meters per second for our velocity. That's hard to visualize, but the flow rate is something we can understand a little bit easier. So when we do our calculations, we need that velocity and we need it in terms of meters per second. When we present our information to people so that they can understand what we're talking about, we might write it in terms of flow rate, which is volume per time, and we give it in units of liters per minute as opposed to meters cubed per second, because a liter per minute is a lot easier for a person to visualize. So now let's finish the problem. We're asked to find the system efficiency. So efficiency, again, is energy out over energy in times 100%. Our energy out is our potential energy, which is weight times height, plus our kinetic energy, which is 1/2 mass times velocity squared, over our electrical energy that's put into the system, which is voltage times current times time, times 100%. So our efficiency is equal to our weight. Remember, weight is mass times gravity. We haven't found our mass yet, so we need to do another side calculation. Mass is equal to volume times density. Our volume was found to be 0.0005 meters cubed, and our density is 1,000 kilograms per meter cubed. As mentioned earlier, density is a material property, and that 1,000 kilograms per meter cubed should not change as long as you are always working with water. If your pump was moving something different than water, then that density would be a different number. When we multiply this out, we get a mass of 0.5 kilograms. So back to our efficiency equation, we have weight, which is mass times gravity, which is 0.5 kilograms times 9.81 meters per second squared. Notice how I'm keeping my units in my problem. It helps me understand how I'm multiplying numbers and that I'm multiplying them correctly. So now I have my mass times my gravity, and I need to multiply it by my height. My height was calculated to be 0.762 meters. And I'm going to add that to my kinetic energy, which is 1/2 mass, which is 0.5 kilograms, times velocity, which was found to be 0.9356 meters per second, and that value is going to be squared, divided by my voltage, which is 12 volts, times my current, which is 1 amp, times my time, which is 30 seconds. And we'll multiply this entire quantity by 100%, so that it's written as a percent value. Take the time to practice plugging these values in your calculator, and I get 1.1% efficient. I like this problem because it really applies everything that we just learned about calculating efficiency. You had to find velocity, you had to do a side calculation in order to find the area, in order to plug that into your velocity equation. You also had to find flow rate. So now you see the power of having flow rate in order to present your information to people. And then in order to find your efficiency, you had to find your mass using another side calculation and then plug it into your efficiency equation. Take your time with these problems. It can seem a little overwhelming because there's a lot of calculations to do, but if you work through it procedurally, it's very easy to follow. It's a methodic way of solving the problem. Look at what you're given, make sure it's in metric system, and then identify what you're trying to find and the equations that you need in order to find it. Additionally, I like this problem because it is very similar to the calculations that you are going to be doing for your pump analysis. It's essentially the same thing. You were given current, voltage, pump head, diameter of the exit tube, and the volume of the fluid. Those are all the things that you're either going to collect or measure when you're doing your pump analysis. And then you're going to have to find the velocity, the flow rate, and the system efficiency, just like we did with this problem for the different values that you calculate for your pump. This is very similar to your pump, and actually the results that you see here of a 1.1% efficiency for this pump discussed in this problem is very close to the efficiency that you're going to see for your pumps when you do the pump analysis.